Welcome back. We're finishing off the notes for 7.1 with logarithmic differentiation. So we reviewed that first property of powers, and I'm actually going to write out the other two, properties of logs. I just came from teaching Algebra 2, and we were talking about all kinds of things, so I'm all exhausted. All right, another two properties of logs. If I have log base b of two things that are being multiplied. So if the argument of my logarithm base b is, I'm going to say x times y, I could rewrite this as the sum of two logs with the same base. So I'm going to say base b. So log base b of x plus log base b of y. And we've gone over these properties before, but in this class, sometimes we have to go one way or the other way. Sometimes we want the argument of our logarithm to be the product of two functions. Sometimes we want to split that into addition. It just depends. You'll see quickly in just a second why we want to use these properties though. All right. The other property involves when we have a log where our argument is a quotient of two functions or two numbers. They don't have to be functions. They could be constant. So let's say log base b of x divided by y. That's going to be the same as log base b of x minus log base b of y. So the order matters here. So the order in which we divide our numerator should become our minuend, which is like that first number in our subtraction statement. Our denominator is what is in our subtrahend, that second number in a subtraction statement. Hope those words gave you a throwback to elementary school. All right, you'll see in just a second where we'll need properties 2 and 3. So these two examples at the top of page 96 illustrate when it would just be so brutal to take a derivative without logarithmic differentiation. We can, but it's nasty. So if f of x is x times the square root of the difference of 3x and 2 divided by x minus 1 squared, if we take that derivative as is, that's going to involve the quotient rule, the chain rule in both the numerator and the denominator, as well as the product rule in the denominator. I'm not saying it's impossible. It's not. I'm just saying it's awful. There's so many opportunities to make mistakes. But we can use logarithmic differentiation to rewrite that expression in terms of sums and differences of logs. And if we do that, it's going to make it much easier in the long run. We just have to be meticulous with our algebraic steps. So for ease of reference, I'm going to rename this function f as y. And I'm going to say y equals f of x. So y equals x times, instead of the square root of 3x minus 2, I'm going to rewrite that as 3x minus 2 to the 1/2 power, because I'm sure we'll have to do that in some step, over x minus 1 squared. Just like before, we're going to take the natural log of both sides. So we get ln of y equals ln of all that junk. So x times the difference 3x minus 2 to the 1/2 power over the difference x minus 1 squared. All right, so if I want to apply any combination of those three properties, I need to look at the argument of my logarithm, the thing I'm taking the natural log of, and think first, okay, is it something to a power? Is it a product? Or is it a quotient? And while it involves all three of those things, overall, this is a quotient. The numerator is this junk on top. The denominator is this junk on bottom. So that first log, well, it's the third log property, but the first one we're going to apply is that when my argument is a quotient, I could rewrite it as the difference of two logs of the same base. So we're using the natural base e, so the natural log of y equals the natural log of the numerator, so x times 3x minus 2 to the 1/2 power, minus the natural log of the denominator, which is x minus 1 squared. All right, so that's going to help, but we still need to simplify this. So now if I look in the first logarithm, if I look at the argument of the first logarithm, I see I still have a product. So I could rewrite that now as a sum of logs. If I look at the argument of my second logarithm, I have an exponent. So I could pull that out in front and make that a constant multiple of the log. All right, so it looks like I'm going to need to start writing smaller since we have so much algebra left to do. All right, the left side isn't changing because we haven't taken the derivative yet, so we just have ln of y. But I'm going to use that product property of logs to break this into the sum of two logs of the same base. So this becomes the natural log of x plus the natural log of 3x minus 2 to the 1/2 power. And then I'm still subtracting from that the natural log of x minus 1 squared, but I'm going to take that 2 out in front using that power property and have that 2 times the natural log of x minus 1. All right, the very last thing I'm going to do is use that power property one more time to get that 1/2 out front. So we get ln of y equals ln of x plus 1/2 ln of 3x minus 2 minus 2 ln of x minus 1. All right, that was all algebra 2. Now we're going to take the derivative, the fun part, probably the easy part. All right, we're taking the derivative with respect to x on both sides of the equation. I know you guys often don't write this one little step. That's fine with me. On the left, we get 1 over y times y prime. Again, that y prime comes in from that implicit step. We're taking the derivative of y with respect to x, which is dy dx, or y prime. And now we have 3 terms to work with instead of just a cluster of factors, or a quotient and also factors. All right, so each term carefully. The natural log of x, that derivative is just 1 over x. Nice. The next one, we got to use the chain rule. We have 1/2, so the 1/2 comes along for the ride, times the natural log of 3x minus 2. So our derivative is 1 over the junk, so 1 over 3x minus 2, times the derivative of the junk, which is just the 3. So that is all the derivative of the second term. I'll try to put these together so we can get that. 1 over x was our first term. And then lastly, our third term, which is minus or negative 2 ln of x minus 1. So that negative 2 is coming along for the ride. 1 over the junk is 1 over x minus 1. The derivative of the junk is just 1. X minus 1's derivative is just 1. All right, so as much as that's tough, it's not nearly as tough as using the product chain and quotient rule in combination as it's written originally. We're not done yet, but we're close. So we want to next isolate y prime by multiplying both sides of this big equation by y. When we do that, we get y prime isolated on the left. On the right, I have in parentheses or brackets 1 over x plus, for the second term, I'm going to rewrite this as 3 over 2 times 3x minus 2. And we can either distribute that 2 or not, but that is not 6x minus 2, that is 6x minus 4. So be mindful of the distributive property. Minus 2 over x minus 1, and then all of that times y. Well, again, we want to get this back in terms of x. So look at what y is. It's all of this that we started with. So all of this times x times 3x minus 2 to the 1/2 power. In fact, I'm going to go ahead and say the square root of, because in our multiple choice answer, if the exponent is 1/2, the AP convention is that they'll write that as a square root, but any other rational exponent will be left so. Okay, can you imagine how crazy of a rule we would have to use to get this in combination of the product quotient and chain rule? It probably wouldn't look just like that, but that is our derivative. And if this is a problem where, like, if this is your answer choice on the AP exam and you see how crazy it looks and you see that original function at the end, that's your key. That crazy derivative is probably a result of logarithmic differentiation. All right, I'm going to do this very last example for one more. If you feel like you're good on that, you could move on, but here's just one more example. All right, we're given y. We're going to jump to taking the natural log of both sides. So x minus 3 squared times x squared minus x, all of that to the fourth. Man, this one's rough. 3x times the square root of x minus 1. All right, using those log properties, the left side doesn't change, ln of y, but the right, again, we've got a quotient. So natural log of the top, that's going to be x minus 3 squared times x squared minus x to the fourth, minus the natural log of the bottom, which is just 3x times, instead of writing that as the square root, I'm going to write x minus 1 to the 1/2 power. Okay, so now if we go back to our first logarithm, we could see the argument is a product of two logs, or a product of two expressions. It's fourth period. You know, my brain doesn't make words easily, fourth period. Right, so we have ln of y equals ln of x minus 3 squared. In fact, I'm going to go ahead and apply that power rule right now and put the 2 out in front, plus ln of x squared minus x to the fourth. Instead of writing that as to the fourth, I'm going to go ahead and apply that power rule, put that 4 out in front, minus, now we need brackets because we're still going to get a sum from the argument of this logarithm, but everything needs to get subtracted. So minus the natural log of 3x plus the natural log of x minus 1 to the 1/2. And I'm going to apply that power property and pull that 1/2 out in front. Okay, if you want to distribute that subtraction over, that's fine too. I would probably do that in the next step before we take the derivative. So far we have the natural log of y equals 2 ln of x minus 3 plus 4 ln of x squared minus x. I'm going to distribute minus ln of 3x and then minus 1/2 ln of x minus 1 since we distributed. All right, as much as that's pretty rough looking, we've got this. We can take the derivative now. Oh, I'm going to have to go out into no man's land. All right, the derivative of the natural log of y, 1 over y times y prime. 2 ln of x minus 3 is going to be 2 times 1 over the junk times the derivative of the junk, which is just 1. We get to the next term, that's going to be 4 times 1 over the junk, x squared minus x, times the derivative of the junk, 2x minus 1. Get to that third term, minus 1 over 3x times the derivative of the junk, which is just 3. And then that fourth term, minus 1/2 times 1 over x minus 1. The derivative of the junk is just 1. Okay, the bell's going to ring in just a second. So here's my quick cleanup step on the right. I'm going to write that as 2 over x minus 3 plus 4 over, no, plus, I'm going to just distribute that 4. So what's that? 8x minus 4 over x squared minus x minus 3 over 3x. Ooh, those 3's cancel. So I'm just going to call that 1 over x minus, and then again, we'd have to distribute that 2. So, or leave it, but don't, it's not 2x minus 1, it's 2x minus 2, or it's 2 times the difference of x and 1. All right, last step. I know I've got students about to meet with me in just a second. Maybe it's one of you. Multiply both sides by y. Our final derivative is going to be all this junk. Ugh. So 2 over x minus 3 plus 8x minus 4 over x squared minus x minus 1 over x minus 1 over 2x minus 2. All that junk times our original expression, which in itself is like super complicated. X minus 3 squared times x squared minus x, all that to the 4th power, divided by 3x times the square root of x minus 1. How much fun is that? All right, honestly, there's nothing else we really need from section 7.1. The tangent line approximations, you could go back to unit 3 when we, or nope, unit 4 probably when we first did that. We could review that in class. We don't need to do that with logarithmic differentiation.